Okay, welcome to video 2 for our 3D modeling class, and now we're getting into sampling. So sampling is a really important concept in creating models, and whether that be creating a map or creating even just like trying to draw out a building, right? How often should you be sampling in order to determine the shape? So there's a lot of like generalization that kind of goes with this as well, but the idea is that we can't infinitely we cannot get an infinite number of points to be able to represent and anything on the ground. So how many points do we need in order to represent the area that we're in? Now, a lot of this is kind of coming after the fact that we've collected data points, because we need to know how the error changes based on the sampling. But with LiDAR, this is really like actually one of the more important components of LiDAR, because when you go out, you're going to collect like millions, if not billions, of points in one project. And in your area, that many points is going to bog down your computer significantly. So, to even like try to run software that can handle that kind of data point, it's almost impossible to find something that can actually process that. So we always have to sample the data set that we have. And so that is really, really important, because again, like even though computers are a lot more powerful now than what they were like 20 years ago, they're still not able to handle the data sets that come out of LiDAR. So we have to sample. And so that is why we get to talk about that today. So here's some examples of sampling techniques, right? So it really is, we're more worried about surface modeling and the sampling techniques for that. But sampling itself comes in many different ways, right? Like if you were to go out to the bar and you wanted to try some beers and you got a flight of beers, you get to try a little tiny glass of it. Do you really get to enjoy the full experience of drinking an entire pint? No, you can't. Like you just won't have that because you only have a little bit. The same with snacks. You're still not going to have a full experience of having a whole smoked salmon on your cucumber slices. You're not going to have that. So with that, even though that maybe that's all that you need, right? Like, so if you're looking at a flight and you're like, okay, I'm going to try all these different beers, you get one you don't like, you only need to drink a little bit of it, right? And even if with these cucumbers, you only need to try one and you're like, hey, you know what, I don't need any more. And that's okay, right? Like the sampling techniques in that way is okay. And so with data points, it's the same idea. I may not need the entire thing to be able to get the model that I need. And how many points do I really truly need in order to get the model that I need, or that I'm creating? So this is called optimal sampling. So how much is enough? Like, for example, if you think of the flights of beer, if you only got a shot glass of every single beer, then you're going to feel like, okay, well, I kind of got the flavor of the last one out of my mouth, but now I haven't had a chance to actually fully enjoy it. So getting a larger glass, but not a huge glass, is better, right? So here's where, what is that optimal sampling amount? So here we go. We have oversampling, undersampling, and then optimal sampling, which kind of falls in between all of that. So here's our land, which is on the top here. That's what it looks like. And then if we undersample it, we end up with this curve that's sort of like just this straight black line. It's like, okay, well, really maybe that's a little bit undersampled. And then we have oversampling, which shows you're really trying to capture every single change, and we're going to draw this and reduce the amount of error entirely. The difference between the two, this one is way more efficient and way more economic. This one is not. And this one's going to take a lot more time to process. It's going to take a lot more mathematics to try to represent it. It needs more data points just in general from the population in order to create this model. So the optimal sampling component of this of oversampling is really challenging. You just can't meet that optimal sampling rate. So a good example here is over and undersampling. So if I take my Arctic work here, and you see how it kind of bumps up and down as it goes. It's almost like little rolling hills. Well, there's my little, 2-kilometer transect. Now if I were to just do a 2-meter transect in here, you're going to see ground that looks like this, which pretty much looks exactly the same. So at what point do I need to capture this 2 meters? Do I need to show all of that variation in here if I'm trying to cover a 2-kilometer transect? Probably not. I had actually a really good conversation with a glacial geomorphologist at one point, which means he studies how glaciers and the ice sheet had formed our land into the shapes that it is right now. Is actually really super fascinating. So, and he was talking about LiDAR, and he was using LiDAR, and he was looking at sampling rates in order to determine like how our land was formed. And so he would go out, and so he was sampling at like 1 meter. So every 1 meter he was looking at data points and modeling that, and came up with a theory. And then he had a sampling rate of, I think it was like every 20 meters. And you know, and looked at that. Then he ended up doing one at like 10 meters, and it showed something entirely different. And so he was able to come up with his new theory, tying those other sampling rates to that like 10-meter sampling rate. A completely different way of actually the ice sheet formed the ground in this particular way, because if we look at these sampling rates, we can connect them in this way. It was really fascinating. So sampling is not just like, you know, just like trying to figure out how many LiDAR data points you want, but it also ties into that application. And you can completely change the scope of the project just by your sampling rates. So there's many different techniques for sampling. So Fourier analysis. Fourier comes up all the time, and this is all remote sensing, so you just gotta love them. It's just the way it goes. There's something called fractal geometry, which is a little bit of what we're going to be looking at. Then there's curvature and covariance and semivariance. So we're not going to be looking at curvature or covariance or semivariance. Those are very statistical analyses of trying to get optimal sampling. But the fractal geometry, we can break it down into some simple analysis tools. So the thing is that originally we need to have samples at a higher frequency than the sample that we want, right? So we need to have pretty much all of our data points first, and then we have to take a small selection of that and like basically cut out like a small area of that higher frequency, and then we would try to come up with that sampling rate from that small selection, so a sub-selection of our data points. And then we'll say, okay, so the rest of this we're going to sample at this rate. So, so looking here at our contours, you can see that the contours are like sampled at certain points. Of course, it makes it really noisy, but that's the oversampling component of it. Then we have here, which I know that I have this big white thing, or yellow banner across here. But so we have undersampled. Maybe this is the model that we're trying to come up with, and this was the original model down here. So we're going to, so you can see how the triangles are much denser in this particular case. And we're trying to come up with an overall model somewhere in between this one and this one, or actually this one down here, and see how the progression comes out. So oversampling and undersampling. And then again, you know, drainage, this one is in particular looking at drainage. As soon as you have drainage application, you know that everything's going to have more samples, because you really need to know to a high degree of accuracy what direction is your ground going, so you know what direction your water is moving. Because that you put one drop on your table and you're going to find out which way it's leaning, right? So it's a very, it needs that very high level of accuracy. Optimal sampling methods. So we're going to look at something called linear interpolation for doing this. This is looking at that fractal geometry, kind of breaking up a line into different components. And so the objective of it is to calculate the optimal sampling density to accurately estimate heights in a DTM. Okay. So we need to have a profile of heights. So like I was saying, you take that little area that you want to measure, and we're going to create a profile, so really going from 3D to 2D, and at a very small sampling interval. So let's say we're going to say 30 centimeters, right? If my population was sampled at every 15 centimeters, let's say 30 centimeters. Then we're going to, then that's going to be delta D. And then we have to know what our required accuracy is. So what does our client actually want? So the RMS error is what we are looking at in this. So these are the 4 steps that kind of come along and come into play. I will do a mathematical example in another video, and I will refer to it as a optimal sampling calculation. So you can actually see it at play. So we're going to calculate the RMS value of the interpolated and known elevations, right? So these are we're going to have, okay, here's my model that I want to use. So this is what the value would be at that point. And then what is the actual known elevation? Okay. Then we're going to plot the RMS values versus the interval on the graph. So again, you'll see a graph of like, here is my observed value, here is my interpolated value. You're going to find out that RMS value between those two. Then you're going to plot them. And what you're going to do too is like that entire profile, you're going to take an average of that entire profile based on the sampling rate. Then you're going to estimate the level of interval for the required accuracy. So you say, okay, you know, I need to have an accuracy of 15 centimeters. So then I figure out where on my graph does it fall within 15 centimeters. And then I use the following equation. So again, I'm going to be going through a mathematical example in another video, so you can be able to watch that. But here's all the kind of the theory behind it. Okay, so this first equation, sigma int is my required accuracy. Okay, so this is what your client says. I need this accuracy to be this. That's it. Whoops. That's up to you to be aware of that. Okay. Then we have a function. This is not RMS value times that. That is not a times. This is a function. So you know how we write f at x, like with f with the brackets and put x in it? F is not multiplied by x. That's not at all what it's showing. This is saying what is the value of the RMS at this point on the graph. And I'll show you this in a moment. So this is k minus 1. K is my sampling kind of counter. And I'll show that in a moment. And then we have sigma d opt, which is my optimal. And then so this is the delta that we're calculating. And k minus 1 plus delta. So this is literally just that number. This is multiplied by your the difference between your different samples. Okay. So let's take a look at this a little bit. So I have my graph. So on the bottom here, I have my delta D. Delta D is my sampling rate. So this one, for example, might be 10 centimeters. And then this point here might be 20 centimeters, and then 30 centimeters, then 40 centimeters, and 50 centimeters. These are going to be equal all the way along. You're going to change it at an equal interval. Then you have the RMSE value that you have placed on the y-axis, right? So I do my sampling rate at 10 centimeters. And then I come across here and I say, okay, this is my RMSE of that data set. And then at 20 centimeters, this is the RMS of the entire data set, the total overall, and so forth all the way up. Okay, so that's the RMS value for each data set, and this is the sampling distance between each of the points all the way along the bottom here. Then we have our RMS, which is k minus 1. So k is my counter, like I said. So the best way to think of it is okay, so we have a starting point, which is like 1, k equals 1, and then k equals 2, k equals 3, k equals 4, and then k equals 5 in this case. So there's k, so k is 5. So in this case, they're saying, oh, this is my average, which is your RMS, right? Like I'm saying my accuracy needs to be 30 centimeters. So if my accuracy needs to be 30 centimeters, I look at the RMS error. I try to find that on the y-axis. I come across to the graph and I find where it's sitting. I can draw it down and say, oh, look, it is between k equals 5 and k minus 1. So that would be 4. Okay. So again, you have to count what interval it is between, because this is interpolation, right? So we're going in between two calculations that we've done. This is my known accuracy that it has to meet. So that is found on my RMS value, and I project it over and I find where is it on the x-axis. So those calculations that we do, remember that I showed that little delta? So this is what you're calculating there, and then what the next calculation does is it projects it down to here. The answer you get is your optimal sampling distance. Okay. All right. So you'll go to a video that is referred to optimal sampling, and I will show you how to mathematically calculate that. And so you'll get to see a better example, but that's just a quick explanation of what's happening. So, so the next thing is roughness factor. So this is another optimal sampling method. This one is actually used in geography a lot. So if you're doing any kind of environmental studies, you're going to end up using a roughness factor. And so this is looking at like the difference between characteristic points. So we have VIPs, very important points. So we have peaks and pits. We have passes, so where things change on either side. We have convex points and concave points. So all 5 of these are VIPs. Now you'll probably get asked about them in an exam. These are really important with roughness factor. So the roughness factor is actually a simpler calculation than the optimal sampling linear interpolation that we just did, or we're just talking about. So you need to find peaks and pits in the profile. So you have a profile again, right? So you go back to heights and you just have a line. And in fact, when I was doing roughness factors of snow, we had a metal chain that was a certain length. And then it was like a 1 meter chain. And then we would drop it down on the ground. And how much it shortened up was how we would calculate roughness factor. So it pretty robust and really pretty, like, you know, almost like primitive in lots of ways. But it did its job, right? So we need to find in this case, we need to find peaks and pits in the profile. And then we're going to calculate the distance between each peak and pit. And that is known as what we call a wavelength in this case. So, and you'll see why in a moment. And then you're going to calculate the change in height between each peak and pit. So, and you have to know whether it's going up or down. And then you're going to determine the optimal sampling distance, and that's the roughness factor. So using that, here's what we get, right? So we have our peaks and we have our pits, and we see another peak and another pit, and up and down. So my optimal sampling distance is all the way along here. So I'm taking my average of all these distances from this peak to this pit, and then this peak to this pit, all the way along. I would add all those up and divide them by 6 in this case. Oops. And then that would be my optimal sampling distance. Then if we wanted to figure out the roughness factor, which is a ratio, I would figure out those distances in the vertical along the y-axis. So I would determine, okay, from here to here, this line to this line, the vertical distance is Z1, and then going from this point to this point, the vertical distance, as you can see here, is Z2, and then Z3 goes down, up and down. Now it says take the delta average. You do need to take the absolute value of this average, because otherwise you could possibly end up with 0, even though it's like up and down, up and down, up and down, like greatly. So make sure you take the absolute value. And then you divide it by your optimal sampling distance. And that will tell you your roughness factor. So it's really just trying to figure out this average versus this average, and it gives us that answer. So again, I will do an example in my sampling example video, so you can see that math. Last but not least, there's something called progressive sampling. And this is getting to be more and more common. Because the computers do all of this stuff, right? So when you come in with LiDAR data, it's really hard to do a lot of this stuff by hand, but I want you to understand what's kind of going on in the background of what's happening. So this is applying different densities of sampling due to the change in complexity of the terrain surface. So we need high image resolution. So this has to be an image or a raster. And then we start with a low density grid, and then we go with an iterative calculation of accuracy. So we have to iterate. So here we go. Here's what they look like. So the first one, so this is grid and then selective. So these are kind of two different ways of approaching it in the start. So grid sampling, everything's all the same size. So you would just have, here's my spatial resolution. I'm going to stick with that, and that's the sampling. So then we would say, okay, this one's green, this one's red, all the way through. Then we have something called selective sampling. So this is manual. You go through and you look at your very important points. You try to identify where those are. And then you link them together in some sort of like network. And you draw that out in different profiles. This is selective sampling is not very widely used because to be able to get your computer to do it is really, really difficult. It works great in the old, analog photogrammetry situation, but doesn't work anymore, not with computers. Then we have progressive sampling, which is what we were talking about. This is automated. So you can say, I want to improve the spatial resolution in certain areas that have very rapidly changing slopes, for example. So here we have a higher density of pixels, and here's lower because it's not as important, for example. Then there's composite sampling as well, and this combines everything. So this is a lot more widely used. So it takes some of the very important points. Here's my break lines. You can think of it as a break line. We can put those in. We can say those are really important. Following that break line, if that break line allows for me to, or showing bigger differences, then we definitely need to make the grid denser in those areas. And then areas that's not as important, we can just leave it, and it's not showing any major change, then we can just leave them empty and leave them as a large grid. So it allows for a little bit more flexibility. It allows for less of an error to happen within automation. So here's automation. This one still has some human interaction with it. So it does take a little bit of skill to work with this one, but it's actually more accurate. You pay more for this, right? So it's more widely used, but the higher accuracies you're trying to get, it becomes money. And there's always a trade-off between accuracy and money. So in this video, I've covered optimal sampling through the calculations through linear interpolation. I've covered the roughness factor, and I've covered progressive sampling. Progressive sampling is all done kind of in the computer, so you guys do some of that with photogrammetry, and I'm just going to allow for the automated progressive sampling to happen within ArcGIS. That's what it does. So we're not going to do anything by hand with progressive sampling, but just to know that there's 4 different kinds that you can do. And we progress from grid, which is just standard, all the way to this combined approach where you can really improve your model using both manual and automated methods combined together through break lines. So our next video, we are going to start getting into actual models.